Hi everyone, welcome to the presentation for SparkCruise. I am Abhishek Roy from Gray Systems Lab at Microsoft. Today I will talk about the workload optimization platform that we have built for Spark clusters at Microsoft. We are in an age where DBA is completely overwhelmed. Traditionally, the databases are located on premise. They rely heavily on experienced DBAs to manage and tune queries with sophisticated admin tools. Today, clouds like Azure offer fully managed database services. In these cloud-based services, the users can simply point to their datasets and start querying with no upfront costs. This has tremendously increased the number of users and workload sizes. Though both DBAs and cloud developers can tune these workloads, but they lack the tools to optimize massive workloads. We have invested a lot in query optimizers, but the query optimizer still processes one query at a time. The queries are assumed to be independent and the same set of rules is applied every time. However, in production workloads, the queries interact. They can have overlapping computations, dependencies in the execution order, and can even share the query template. There are many optimization opportunities across workload, and optimizing the workload will reduce the total cost for user. Now to make this journey from query optimizer to workload optimizer, we need a workload-based feedback loop. We can learn models from past query workloads and apply them again in future. The workload-based feedback needs to be continuous to handle changes in workloads and datasets. Now we will describe how we added workload-based feedback loop in Spark. First, our telemetry modules captures Spark SQL query plans. The telemetry module collects plan in JSON format and annotates identifiers called signatures at each operator in the query plan. We also remove any personally identifiable information in plans such as table names, column names, and literal values. These anonymized plans and runtime metrics are then collected for cluster level and service level analysis. The collected workload goes through a set of pre-processing steps to generate a tabular workload representation for optimization algorithms. The steps include linking logical and physical query plans with stages in the Spark job execution and cleaning the workload logs for missing or invalid values. The workload processing is run over large volumes of workload in a distributed manner using Spark itself for scaling out the pre-processing tasks. Note that the pre-processing is done once and shared across all of the downstream algorithms and optimizations. Then, the generated workload table can be used to derive better understanding and insights. SparkCruise provides a workload insights notebook to end users and service operators to quickly analyze their workloads. The workload table is also provided as input to optimization algorithms such as view selection. Finally, the feedback generated by the workload optimization algorithms is loaded into Spark Optimizer through custom optimizer extensions. The extensions also contain the logic to perform the actual optimization action. These components allow us to instance optimize the Spark performance for a given workload. Please refer to our full paper for details about each component of the pipeline. We use the Workload Insights notebook to compare TPC-DS benchmark and production Spark workload. The production workload dataset is a mix of around 350,000 streaming and analytical queries. In this workload, 30% of users have hundreds of Spark applications per cluster. There is skew in distribution of queries per Spark application. Most Spark applications have less than 10 queries, while 5% have queries in double digits. Now let us analyze the input sizes processed by queries. In production workload, 30% of input tables have less than 1000 rows. And 60% of queries in production process more than 10,000 rows. In TPC-DS benchmark, almost every query processes more than 10,000 rows. We now dig into the logical operators seen in our Spark SQL workloads. We see that there are 3 times more aggregates and fewer joins in production workloads compared to TPC-DS benchmark. Now let us look at query plan sizes. Plans in TPC-DS benchmark are big. 20% of queries have more than 50 operators. In production workload, 20% of queries have more than 4 operators. In TPC-DS, plan depth is more than 10 for 90% of queries, while in production workload, plan depth is more than 10 for 10% of queries. We have shared the detailed analysis of production workloads in our full paper. Let us look at a specific problem of computation reuse in query workloads. In this problem, the parts of computation are duplicated across multiple queries. The automatic view selection, materialization, and reuse in SparkCruise works as follows. Consider the following 2 queries with a repeated join. SparkCruise can automatically identify common computations of high utility, such as this common join operator. Then once we enable our feature and the first query is run on newer datasets, it will automatically materialize the result of the common join operator, and the second query will be able to directly read the materialized output instead of computing it again. None of these steps require any active involvement by the users. SparkCruise is also robust to changes in the workload. For example, here the filter changed from August 19 on day 1 to August 20 on day 2, and SparkCruise was able to handle this change. SparkCruise can be configured with different permutations of view selection and materializations being either offline or online. The view matching and reuse is always automatic since it is not trivial for end users to manually change their queries. In the default setting, SparkCruise performs offline view selection and online view materialization. Online view materialization does not require offline cycles to materialize views. This makes it a good fit for serverless systems where users spin up clusters on demand, or for recurring workloads that are scheduled immediately after the input becomes available. We also encountered many challenges during integration with Spark Optimizer. For example, optimizing view scans, interference from other Spark rules, and detecting changes in underlying data. Note that currently SparkCruise handles only recurring workloads. We also developed an experimental prototype to target non-recurring or interactive workloads. For the interactive workload scenario, we designed an online view selection algorithm that can select and evict sub-expressions based on the evolving workloads. The details of online view selection are in the full paper. Finally, to summarize our efforts, we believe that there are many optimization opportunities across workloads. In this year's VLDB conference, we presented 2 workload-aware algorithms, SparkCruise and Auto Executor. Going ahead, we plan to build more workload-aware algorithms on top of the SparkCruise platform at Microsoft. Thank you for watching this presentation.